How did I end up here? Well, let's see. All right, welcome to the channel. I've been doing a few videos about phasers, and today I'm gonna try to incorporate some different component to act as a variable resistor. In this video, I'm just gonna go through measurements and how to use optocouplers in as a variable resistors, and then in next videos I'll be working on how to use it and what to do with that. Okay, let's get going. Had a few videos where we were looking into phase 45 like circuit. We use JFETs for the variable resistors, essentially to together they were sweeping the frequency to get us that phaser sound. But a lot of this circuit responsibility of it was to get our JFETs to work exactly as we want them. This is just a small part of the circuit, but you know, like VREF and LFO and all of that had to be properly set up for this to work. So the major part of the circuit is this, well, the biggest part is this all-pass filter. And as you can see here, I made it a bit, I simplified this circuit, just got here this two variable resistors, and I changed their values here on this LT-SPICE diagram. And I used phase 90 simplified circuit a bit. It's slightly less complicated. Later on in phase 45, there were additional components added to make it more linear or whatever. But the idea here is the first all-pass filter shifts phase by 90 degrees at a certain point, and the second also at that frequency. So that's why these two, I point to these resistors, but these are JFETs. In the real circuit, they have to be matched. So at the same frequency, they do this phase shift by 90 degrees. So we have 180 degrees shift, and then when we mix with the original signal, when we mix them, because there's 180 degree shift, they cancel each other. We get a notch kind of there. So if I run it here and I look at my output and get rid of the phase here, you can see for various values for these resistors, we get notches going. Like you can imagine if as oscillator is changing the resistance of the JFET, this sweeps. Okay. But we could use different components for this, you know. I have an interesting one here. This is Optocoupler. I got it, I think, from Farnell. This is an optocoupler. And you can see here, this one is using photocell or light-dependent resistor here at the output. And this is what we want, because what optocouplers are, also called optoisolators, they're isolating two parts of the circuit. So essentially on one side we have something that emits light component, and this is LED, and on the other side we have some component that is reacting to this light and turns on and off this side. So this way these two parts of the circuit are essentially isolated. But there are various different things that you can use for this optocoupler. You know, common type are these with phototransistor, and we won't be looking at that. There are photodiodes, there's other stuff, but we're looking at photoresistors because that's what we're gonna look into, you know. So if you look at resistive opto isolators. It's interesting. These ones were kind of old ones. They were, what are they saying? Like they go back all the way to 1870s, etc., etc. If you look at Wikipedia and you scroll down, there's interesting stuff like how are they used in applications, and they even mention in guitar amplifiers they were used back in the day. We're talking about 1955 here, that were used to create tremolo effect. Now, I said I have interesting component here. This really means I was shopping some time ago for something else, I'm guessing, and I just picked them up. Here, if we look into the datasheet of these components, you can see there is a photocell, and this is kind of a what acts as a resistor, light dependent resistor, and we have LED, and we can look into various things here. In our datasheet, but this datasheet is pretty basic. It doesn't give us a lot. It turns out there are two types of these NSL-32 Optocouplers, and I have both. I got both. This one shows here how this resistance actually is dependent based on the current through LED. So this is important because this is not on-off. There is a certain resistance, kind of a range that we get depending on the current that we can get through this LED. Now, before we go further with this, and then try to understand what these things do, let's kind of characterize our all-pass filters, right? Because I don't really know, if you think about it, we have these, let's say, variable resistors, but we don't really know what is the range of these values here. We know that the maximum is 24K here when the JFET is turned off, but that's about it. Everything else is we know it's lower than 24K. So let's look into all-pass filters, and it's quite... You can have a look at that at your own leisure, but there are various ways to create this op-amp filter. You can do it with low-pass filter, and you can then vary this resistance, for example, because its capacitance is a bit tricky to vary. But if you do this with this resistor, you can do it that way, but we are using a different topology. We are using all-pass filter with high-pass filter. And this is pretty similar to what we have. The idea is that you see here, the filter has unity gain, which is what we want, but it introduces a different delay at each frequency to create this phase shift. And phase shift of 90 degrees, this is what we want, because ultimately we want 180 degrees. 180 degrees is, if you think about it, it's just inverted. If our signal is sinus function, at maximum it would be positive. If you shift that by 180 degrees, you get negative, the same value, and they cancel each other out. So the 90 degrees phase shift happens at this point, right? So 1 over RC. So this is not really useful for us, but just look into corner frequency. If you look at the corner frequency, actually, this is at this input frequency. So it's like 2p over RC. So so we can see that if we fix this C, we can first of all set our frequency based on capacitance or resistance, so we can vary this C if we want to, but in this case, we can choose different values. In the original circuit, it's 47 nano, and we'll keep it for whatever we're doing at the moment. But you're not limited to this. You just need to know this kind of a relationship. So if I created a nice little spreadsheet for this. So here I have different resistances, essentially, and here I have my, as you can see here, I put capacitance 47 nanofarads. Doesn't look that pretty, but here I put resistance, and we'll see what is the frequency at which it generates our 180 degree shift. Again, 90 degrees phase shift, but we have two components. So here it's 1/2 times pi times this is capacitance, and then I have this resistance here, right? So if I look at it here, this is 112 kilohertz, right? So if I at 30 ohms, and I deliberately put it all the way to 100K here, and this is now just using A5, A6, and it's going to use these frequencies. So we can see that at 30 ohms, our shift is at around 112 kilohertz. That notch happens, not notch filter, but notch happens there. And here it's 34 kilohertz, 6.47K, and 3.4, and it all the way to 33 hertz. But we needed to limit this here because at one point the JFET is going to turn itself off, and we're going to end up with maybe this all-pass filter not really working properly. So 24K is the limit, but this also introduces, and again, I know this is phase 90, but it's similar in Spirit, I suppose. It's phase 45, and this just makes the maths simpler. So this is actually in parallel. So if I change this slightly, and I do this, I did this. This is resistance in parallel of this R plus 24K. So we have slightly less resistance because in parallel it's always going to be slightly less than the smallest resistor. And I'm just going to sweep this here. So we can see that in parallel we always have slightly smaller, and then it affects the resistance way more when we get to 10K or even 24K. You see, like it's at half, and it goes towards 24K, never reaches it. But like if you turn off JFET, it is at 24. And then here we see frequency that we expect to see when we run the simulation. And do we get that? Let's see. So let's see if I can make this look a bit easier to follow. So here we can see legend, and we can see 30 is at green and 30 is here. So it's over 100 kilohertz. Yeah, makes sense. It's over 100 when we have 30, right? 30 ohms. If we go and then check, 100, 500, 1K, 3K, 5, 10, 100K, and 1 meg. And 1 meg ohm, I just put it there so it converges to this kind of a value here. So let's see. 30 is about 113. We have now, the next one is 100. Okay, you can't see this because look at here. It will tell you the frequency, and we are talking about 32 kilohertz, right? And it's about right 34 in our calculation there. And like if I, this is not at the right place. Maybe it's slightly here. This kind of a spike. Keep in mind that this is like discrete intervals for this sweep, so could be anywhere in between here, right? So here we have the next one is, I think, 500, is it? It's about 7K. Yeah, pretty spot on here. 3.5K, 3.5K. Here it's easier, because it goes all the way down. So 1.2 for 1.269, etc., etc. So we here, we look at here 500 and 480, etc., etc. So what we're trying to get here, what I'm trying to get here is that realistically, we don't care about anything over 15 kilohertz, 20 kilohertz. So that would be what? 100 is 34 kilohertz. That is too much. So we talk about, let's say, 200 ohms to maybe, let's say, we want to get to 24. So I'm looking here, and this is 174 hertz. 140 is realistically that what we can get, with this circuit. So let's say we're talking about, say, 24K. So let me write it down. So what we expect, what we want to get from our optocoupler is from, say, 200 to, say, 24K resistance, right? And now let's have a look into the datasheet and see if we can get that. So here I can see straight away that this R3 version has you see here at 0.1 it goes way down below 10K. So let's see here what we can get. On resistance is 60 ohms, and when 20 milliamps is the current through LED. Typical on resistance for 5 milliamps is 150. So what this tells me is that, we don't need to go all the way to 20 milliamps, because at 5 milliamps, it might have the limit of what we need to achieve. But obviously, this is meant to be driven by 20 milliamps, this LED, and then you get the lowest, I suppose, on resistance. And keep in mind, this is maximum. It can go probably lower than that. And we'll obviously need to measure this, and it's not ideal, but again, funnily enough, you need to match these as well, like we had to do with JFETs. But this one, maximum forward current for this LED is like 25 milliamps. If I look at it here, and the only reason I was looking there was I had that diagram. Here you can see that the forward current is 40 milliamps maximum. And we're talking about, you'll see we don't really care that much about this forward voltage. We still need to worry about it, but we don't care that much. But what we care about is on resistance 500 is the max, and off resistance is about 500K. Okay, so we still have some resistance, it seems, and this is minimum, so it could be really anything. 500, pick a number, mega ohms or whatever. So what this tells me is that we might need to use this version for our resistance. Again, I want to clarify, we could change the capacitance, and that would affect how we do this. Let me see where my spreadsheet is. I lost it somewhere. I think it's here. Okay. So I could change here and say 22, for example. and all of a sudden we have different here. You see, we can change it, and all of a sudden with 22 nano, these values go up. This frequency goes up, okay? Because if you think about it, this is in reverse proportion to the capacitance. So higher the capacitance, lower the frequency, lower the capacitance, higher the frequency. So, but what I want to do is, because I already have, and we tried it out with 47 nanofarads. We tried it already, and I have the circuit there to try it out. We can try it out with JFETs and this. So that's why I keep saying this is the resistance we're looking for, right? So what we need to do now is actually measure this resistance, because it will be different, unfortunately. Unfortunately for us, because it makes our job harder, we need to do the measurement. There are some other optocouplers that we could use. You know, there's this VTL5C3 or similar ones that have higher on resistance, and that might be. But again, as you've seen, if we know how to use what are the circuits that we're looking for and what their role is in the circuit, we could essentially make it work with different components. Okay, so this is our circuit we're going to use for measurement. So I'm gonna try to fit everything in. It's a bit busy, but you know, as everything else, when you measure these things, there are wires everywhere, apparently. So here, what we have is, in the middle, I have NSL-32. It has a little dot, I don't know if you can see it here. It's a little dot here that shows where cathode is of this LED on this side. I connected it, so at the top there's 200 ohm resistor, there's 100K potentiometer here. It's linear. Then it's LED side of the optocoupler, and now there's 100 ohms here. And I connected that, so I connected green one to ground, and I'm gonna just connect it here, so I'm always, you know, my black probe is at ground, and then I'm gonna just change my red probe. I'm gonna connect it to this yellow one, to the white one. So white one here measures voltage over this 100 ohm resistor. If I want to measure current, I would have to rewire it. It's way much bigger pain to do it. So I'm just gonna measure here, and my current is whatever I measure here over 100, right? So I'm just gonna do this, measure it, take down the voltage. Now I have here on the other side, I have LEDs there just so we can see that something's happening. That's all why it's there. Eye candy, if you will. But how am I going to measure the current through this one? It's going to be the same as over this current through this resistor, right? The current goes whichever way it goes. But it's the same current that flows through the NSL-32, the resistive part of it. So again, I'm gonna measure voltage here. That's my black one, right? Measure it, measure voltage, and that's, I divide that by 100. That's my current. Now voltage, I'm gonna measure by deducting voltage from here. Voltage from here minus voltage from here, I get voltage across here. That's my yellow thingy here. So how am I going to measure this? I created, again, spreadsheet, Lots of spreadsheets today. So I just put a note here for myself. What is what, right? And here, voltage on white. I'm gonna just enter it here. That will give me the input current. You see, A3 over 100. Black voltage, I'm gonna measure that. That's gonna give me output current, C3 over 100. Yellow voltage here, that's the cathode. And then this is voltage over NSL, pins 3 and 4. This is E3 minus C3, E3 yellow minus black voltage, as I was explaining. And then resistance is voltage here over current, right? So let me get going with this, and I'll probably speed it up. So I'm just gonna measure voltage here. It's gonna be very small when we start, because we're gonna start with very small voltages, and thus currents, but hope this is visible here. So I'm just gonna plug this in. Oh, you see it's open. Oh, I need to, okay. You see that? And it's actually the lowest at the resistance all the way up. But this means that we start from here with the lowest current. So just a note on the values there. I forgot to say, the reason why I chose this, first of all, this is just current limiting for LED resistor. Doesn't really matter. 100 just ease of calculation, right? Here, 200 minimum resistance here is going to be 200 plus 100. So that is what we're talking about, is 300 ohms over 9 volts. So minimum. Now there's a voltage drop, so we'll be fine here. So it's going to be, voltage drop is like 2 volts or something like that here. So that's 7 volts over 300. What is that going to be? You do the maths. But it's going to be like 20 something milliamps. So we are keeping it within the maximum here, 25 milliamps. Okay, so that's the reason why I chose these. You can go with higher here. Turns out, because we are only caring about certain, we don't care about 30, 40, 60, 100 ohms resistance. So this current is going to end up being very small. So let's do this real quick. So here at the very smallest, this is what? 7.7 millivolts. Okay. How do I enter this? That's 0.0077, right? Oops. Okay, black. It's 11 millivolts. So that's 0.011. So this is our current. So output current is 0.11 milliamps. So input current is 0.08 milliamps. It's quite low, but we can still see that there is some output current. And what is yellow voltage is what? There's my probe. We need to increase this. Increase it more. 678 volts. So resistance is like at the lowest that we could get here from this circuit level is 62K. So this is good. So minimum is over what we want. We want 24K. Right? So let me go and just do this. I'm just going to increase this measure, and I'm going to try to keep it reasonable values here. It's going to take a bit, so I'm going to speed this up. And obviously I'm going to then do it for the other ones. A word of advice, just write some number on them, so you know which one is which. So let's do this real quick. And that's it for this one. We ended up, and you can see that this the current here goes very slow, and we can control it for the vast majority of the range, and then it gets very quickly to currents that we don't really can't really control them properly, because very small change here makes a huge, change on the current. But if you look at here, really we are talking about the resistance starts at 61, 62K, drops to 37, and we're talking about just this is here it's 0.1 milliamps. This is 0.2, and this is 0.5. This is 1 milliamp. This is nearly 2 milliamps. So at 2 milliamps we have 584. At 15 milliamps we have 121. So we just need to find out, at which point we have about 200. But in reality, 2 milliamps might be enough for what we need it for. Probably not. 500 is here, that's 7 kilohertz, so even that would be relatively, should be looking, it's a bit more than, a bit less than that, I suppose. We can go lower, but the minimum is 121, so we could go a slightly bit lower than this, so that would be maybe 3 milliamps. But I really can't get this to work. And again, I could have done this with 10 kilo ohms, but it would be I would get a very big sweep in terms of maybe current here. It would be easier sweep, but it wouldn't make a huge difference, because you can see here between what is this, 14, between let's say 2 milliamps and 18 milliamps. It's very small. Depends on what you need it for. You might get this, instead of doing 100K here, you put maybe 10K potentiometer, and then you add an additional resistor here. So what I'm going to do is I'm just going to go through this for all of them, and let's see what we get. Okay, after finally going through all of this, I measured everything. So we can see here I have 6 different devices. 2 of them are this NSL-32 SR3, and while they're pretty similar matched, but they start only at 1.3K, 1.8K, and they have very little, 29 ohm. It's not very little compared to, say, something like MOSFETs or something like that you could use as a switch, but still relative to the other ones. So they won't really cut it, because we need a higher, let's say, starting resistance. But you can see here number 3 and number 4 are not that close. Actually, if I look at number 2 and number 3, they are closer. So number 2 and number 3 are closer to each other, and number 4 and number 1. I suppose I'll go with this one, because it just gives me a bit more room to operate, because they start with 42K, for example, from this other measurement, and they go 148. So this is pretty much what we're going to use. Now, keep in mind that this is 0.07 milliamps. So this is 0.1 milliamp. So we need to come up with a circuit to actually be able to use this. So that's what I'm going to do next. But the first part was to use to measure them, and now I'm going to mark these two. I'm going to use them in my circuit. Until next time.